Hi, everyone. Today we're going to be talking about automatic analog IC placement and layout. I'm Nathan.
And I'm Peter.
So, a quick introduction. As we've kind of talked about in class, the design of analog circuits typically is known to rely heavily on expert heuristics, right? Which means they typically have to take into account some type of caution when it comes to creating it. They have to look at things like symmetry, noise, parasitics, and it really means that you need these system design experts in order to create circuits. It's not very uh, good at involving new engineers who might not be aware of how the design comes to fruition. We aim to explore how LLMs could potentially close this gap and remove the need for system experts and lower the barrier of entry to designing analog circuits. And so what we're going to propose is a main question of how can we take advantage LLMs in order to design circuits from scratch. So a lot of today's implementations that we've seen before typically work off of circuit netlists, designer constraints, or other forms of uh, inputs. However, we want to avoid the use of any aforementioned constraints. So we're going to rely solely on human natural language and feedback in order to create circuits. So here is our overall system architecture. And so to quickly go through it, we start again with natural human language. So user prompt. For example, it might be something like create a simple differential amplifier, right? In this architecture, we use two rags as well in conjunction with our input, which will house a variety of data in both rags. Then we send in a prompt to GPT-4. We generate what's called strict syntax, which we'll dive further into. And we use a knowledge graph in order to enforce certain constraints. Once we have strict syntax generated from GPT-4, we use something called Glayout in order to create parameters and commands in order to create the actual placement and layout and creation of our circuit. And then finally, we involve user feedback in order to help refine the circuit more to what the designer intended. And lastly, we're able to get our GDS2 output.
Okay, so for this system, first we start with the system input. So compared to, let's say, with Magical or Align, with Magical or Align, you typically start with the netlist and then it outputs the GTSII. But in this system, we can just input some random sentence. Let's say I want to design an amplifier, and then the system uses GPT-4 to create the netlist itself, and then it uses glayout to create the layout. So in this system, um, we use two rags. Uh, so the GPT-4 prompt in here, when the user inputted, the GPT-4 prompt is being modified such that one we can um, it can be used for the strict syntax used for the G layout, but also to generate the circuit netlist. As you can see, there's two rags. The first rag is for expert heuristics. So in this, the expert heuristics gives some recommendation on how to design an analog circuit, and it just gives the top three data or uh, top three relevant pieces to design a nano circuit. And the second rack is for the strict syntax. The strict syntax would be for input to the G layout so that it can design the analog layout for that specific circuit.
So once the prompt has been set based off of RAG 1, RAG 2, and the strict layout instructions, we use a knowledge graph to enforce for what we call legality. And so we go ahead and look to the picture shown over here. we're now talking about what's called the knowledge graph. So this whole time we're trying to prompt GPT-4 into creating strict syntax. It's a form of syntax that GLayout will take and be able to create our circuit similar to how Pierre mentioned. However, as many of you might know, LLMs tend to have a problem with things like hallucination. And even with the use of RAGs, that's what we encountered. We wouldn't get the strict syntax that needed and adhered to what GLayout expected. So we built a knowledge graph that, again, would enforce what we call legality. So it's essentially built on a database of all the legal components and their dependencies. So, as an example, an op-amp might be made up of a variety of different components with that in G layout. For example, an F integrator, an S integrator. And in our knowledge graph, we build that up and interconnect the main component. For example, this would be an op-amp, and we relate it to every other component it might be related to. And we do this for every single component. And so once GPT-4 creates the strict syntax, we compare it against this knowledge graph. And if GPT-4 used a legal component, this means that nothing was hallucinated, right? And we can continue on with our system as expected. But if GPT-4 used a component that does not exist, we reference it against the knowledge graph, and we essentially guide GPT-4 into saying kind of like, hey, this component doesn't work. Here's some components that you might have tried to use using semantic similarity. And then we refer that to GPT-4. So that's where semantic similarity comes from on bullet point 3. So if GPT-4 said, for example, multi-stage op-amp, which doesn't exist, we'll reference that to the knowledge graph and maybe find op-amp and tell it op-amp is a legal import. These are its dependencies, and we'll essentially refer other things that it can possibly use with what it attempted. And we found that this method gave us really good strict syntax generated for us to use and send off to GLayout. And so to give a little bit of context onto what strict syntax is, once GPT-4 has now generated the legal strict syntax cross-referenced against the knowledge graph, it has to be parsed. And so this is a fairly trivial problem. It's not difficult, right? Here's an example of what strict syntax actually looks like. For example, you might have an import at the top, so class B push pull, or sorry, that's the name of the component. You might have no imports. You'll create your parameters, right? So the width, the length, any multipliers you might need, the type of parameter it is. So maybe it's an int, a float. And then you have to actually specify how you want this place moved and routed relative to one component to another. And so this is all what we're really aiming for GPT-4 to generate. And once it does, we pretty much have to parse it. And again, that's a very simple problem to solve. We just use some regex within our code. But the important part here is that, again, the create command essentially creates a parameter. The place places a component with parameters. Move moves a component, which can be absolute or relative move. Route uses a smart router to route between components, and import lets us use some pre-existing libraries within GLayout. And so this is really what we're aiming for, so we can send it off into GLayout to have our final outputs.
So after we created, as Nathan said, the creation of the parameters for the G layout, um, this the GPT-4 will create a new function, a new file just for the definition file. So it includes the PDK. Let's say you can use the Global Foundries or the Skyworks, and then you have the parameters created by the GPT-4. And of course, uh, as mentioned, to avoid the need for system experts, we prompt GPT-4 to populate the parameters. And because GPT-4 also um, not perfect, we include a feedback. So this feedback is allowed for the users to specify a certain parameter. So let's say um, the GPT-4 let's say the user wants to change the input width of a certain component. It can just say Oh, we can just type in the user wants to change the input width to 4, probably. Of course, uh, next slide. Uh, oh yeah. So after the users specify the changes, it'll it'll show a new generated parameters, and it'll show the new um, parameters values as well. And of course, here are the results. Uh,
Right. So let's say now the designer has populated the results and gives GPT-4 the feedback with those results, or sorry, with those parameters, gives feedback about the parameters. Then we end up with the final results. And so we did end up with some pretty interesting results. And we essentially attempted this by splitting up with essentially easy, medium, and harder, or what we consider easy, medium, and harder circuits for GPT-4 maybe to interpret and design. Um, and so here we have two of what we consider on the easy, right? So for example, the user prompt here was create a simple differential amplifier using two matched NMOS transistors as the input pair. So we're not very vague with our instructions, right? We tell it what kind of transistors to use, what is the main circuit that we want. We tell it to keep it simple. And so as you see in the results, we essentially have two NMOS with GPT-4 populated parameters that were routed together and created and placed. And so we do the same with a simple current mirror with two matched PMOS transistors, and we have the same result. And so we can move on and show, for example, what we consider medium. So create a folded cascode, I think that should be cascade amplifier for high gain and output swing. And so we're a little more vague with it. And again, we're able to get some pretty decent results from GPT-4. Now, the system, of course, isn't perfect. So if you look at the final, what we consider hard, the prompt would be something like create a strong arm latch using interdigitated placement to match the cross-coupled inverters. And so it's not an inherently hard circuit, and we're kind of descriptive with it. But due to the limitations of our data, we're actually able to get placement and the creation of our components, but we're not able to get full routing because the placement of the components might not be ideal for, in this case, Glayout Smart Router. But we're able to get somewhat close to what we wanted, which we're pretty happy with, right? And so that leads us on to our future work. And so a big issue that we had was that our RAG data sets, we believe, were not large enough to cover what we really wanted to cover. So for example, we had our two RAGs, right? We had RAGs on strict syntax, which was fairly well covered thanks to Glayout's already existing data. But then we didn't have a large data set for actual designer heuristics. And I believe that we would have had better analog design data, so actual information on how to design analog circuits, we definitely would have better outputs in our system. Second, for future work is to include knowledge and constraints graphs for design rules and designer heuristics. So right now we're kind of relying on GPT-4 and our knowledge graph to kind of generate within certain, well, not even within certain constraints, right? We left it kind of open-ended as new designers, but we would ideally like to be able to push GPT-4 to be further constrained to things like design rules. And lastly, feedback from simulation would be great. So right now we have feedback from people, right, which can give the designer the ability to kind of give what their intent is to GPT-4. But if we were able to simulate and then feed back to GPT-4 some kind of improvements that we'd like to see after simulation, that would be great for this future work. And so that's all we have, and we're going to go ahead and move on to a demo.